You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that had, has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and share it with friends. Thank you. Hello, this is Richard Jacobs with the Future Tech and Future Tech Health Podcast. I have Elizabeth Parrish. She's the CEO of a company called BioViva, and they're committed to extending healthy lifespans using cell technologies. So, Elizabeth, thanks for coming. How are you doing today?
Hey, thanks for having me. I'm doing well. It's nice that we're having this conversation.
I hope just by talking to you that this will extend and improve my lifespan, even just a little bit. But we'll see.
I think it will, because I think you're going to get really excited about the future. So there's two things that we can do. There's one thing that we're working on, and that's genetically modifying humans, and that's our company's goal. Modifying them to be healthier, maybe stronger, faster, smarter. So it's pretty exciting. But the other thing in the medicine world is the placebo effect. And so I'm hoping that the placebo effect of just sheer excitement about this technology hits you first. And therefore extends your lifespan some amount of time, and then we can use the really strong technology to do the rest.
It was interesting. There's a famous entrepreneurial coach. His name is Dan Sullivan, and he asks entrepreneurs, how long do you think you're going to live? And, a lot of them will say 80, 85. So he'll say, okay, 85. What's it going to be like for you when you're 84? And he said most of the people will say, I'll be, I'll have grandchildren, I will still be working, or I'll be doing this, I'll be busy, So he says, well, if that's what's going to happen when you're 84 and you're going to pass at 85, why within that 1 year would things all of a sudden fall apart? And people say to him, I don't know, maybe they wouldn't. So then he asks them later on, after they go through the exercise, well, maybe you'll live longer. So he a lot of people will say, well, I think maybe I'll live to 100. So he tells them, congratulations, I just gave you 15 more years. By thinking that,
yeah, exactly. I think that one of the missteps that we make, and it's probably because of, the myths we live by, and I talk a lot when I talk publicly about breaking down myths that we live by, because they really hinder our chances of success. So saying things like dying of aging is natural, and that's just how things happen. Well, actually, that's a multitude of myths. Number one, most people didn't die of aging before antibiotics and immunization. And, dying of aging is as natural as dying of cancer and heart disease and all sorts of things that we want to cure. And so those are the things that we're actually looking at. Another misstep that people make is thinking that at some point in time, they will be excited about dying somehow. And you're right. So if somebody said, I only want to live to my 101st birthday, well, how are they going to feel the day before that? Unless they're in excruciating amount of pain, in which people do tend to start letting go, or cognitive decline when they're not thinking clearly anymore, or we know another state is massive depression. People generally want to live. That it's in every species on the planet is self-preservation. And so to think that we somehow are better than that, and that we wouldn't still want to be alive and have our most valuable and best asset of being a living being on the planet is just absurd. And so the first thing to do is to break down those sort of basic myths of at some point I will be happy to die. It's not in line with an organism's survival to think that way. And so we project it off into the future. And that's how we sort of create this illusion of strength and being satisfied with that. What I would rather be satisfied with, so when people say, well, I'm going to die of aging someday anyway, and that sounds very brave and bold, I'd rather see people coming up and testing technologies and being able and deciding to take a risk today to make the world a better place tomorrow.
Well, we'll get to the technology in just a second, but have you spoken to people that are, 75, 80, plus, and have you asked them how they feel about their life? That do they feel like they're about to go, or, I don't want to ask anyone that age that because I feel like it's, extremely rude, and I don't even know if I want to know the answer, but I have people in my life that are older. I'm sure you do. And I wonder, what are they thinking and feeling at that age? I mean, I'm in my early 40s. Hopefully, I won't have to worry about it for a while, but I've always wondered that. I don't know if you've thought about that.
Yeah, so I talk to a lot of people who are aging. I talk to a lot of people who are, over the age of 65, and 65 can still be really quite viable if people are active and eating well. But for some people, they have detrimental health. I've talked to people in their 70s and in their 80s, and what all of them say is that inside they feel like the same person they were when they were a kid. Their body is just giving up on them. Their body is deteriorating around them. And it's a really perplexing thing. In the world of men and women, men don't, age well and women don't. Quite honestly, both sexes become invisible to the other sex, or if they don't identify with the same sex sexually. There's a lot of loss and grief and things that help them sort of phase out and maybe come to terms with things, but none of them want to die. I mean, I have been to both religious groups and agnostic groups, and they all think that living would be the number one thing that they would like to do if they could be healthy and strong and live long.
Okay, well, very good. I appreciate your insights.
Well, we also see that in medical diagnosis. I mean, whether people are highly religious or they're not highly religious, people spend almost all of their money on health care when they've been diagnosed with an end-stage disease. So we know that people put everything into trying to stay alive. Once pushed up against the wall, what we want people to do is act before they get to that point.
Makes sense, yeah. So let's get into the technology of it. So what have you decided is going to be the mechanism by which you're going to help people to live longer?
Well, so from 2011 to 2013, I was volunteering for a stem cell nonprofit, and it literally was just to try to help get some amount of education out there so that stem cell use could get funded. So when the Bush administration shut down funding to embryonic stem cells, it appeared that everyone in the world thought that stem cells meant embryonic stem cells. And they thought, and really, that the use of embryonic stem cells has been minute. 99% of the use of stem cells at that point were autologous stem cells, meaning stem cells from your own body. And so the listeners know stem cells have the ability to regenerate certain areas. They send off certain exosomes that today we're looking at more than stem cells, these little exosomes, injecting them into systems, creating regeneration. They heal wounds. They can regenerate organs. They can actually grow organs at Wake Forest with stem cells. The patient's own stem cells reject an organ when you get a transplant. Now, only simple organs, not complex organs. So it was a really exciting field, and I got brought in to help put together an educational platform and teach people what actually was happening in the industry. But during that time, what we found out was all of the research looked really great from places like Harvard and Stanford, but there was a big debate about what doctors were doing offshore. There were testimonials of people with chronic kidney disease who had, been put into better states of their condition. And there was a big debate as to whether this was credible work. And so towards the end of that project, I was trying to mix medical doctors with researchers. And then I'll end up jumping forward to that's exactly what we do now, but with gene therapy. So I spent a couple of years doing that. In 2013, my son was diagnosed with type 1 diabetes, and I'd spent 2 years looking at regenerative medicine, was thrown into the hospital with him, and I asked them about, what did they have in stem cells and biobanking, and they said, that's experimental medicine. We don't do that with kids. And they said, you should consider yourself lucky because your child has a manageable disease. Some kids here are dying. And that was it. That changed the course of my life. I quit the stem cells and I went on a search for patient advocacy. How do we get access to people? Why do we let people die without accessing technology that in both research and in offshore use, the technology was showing promise, any promise? Why would we let people lose their biggest asset? And so when I got into this, I was simply looking for cures for kids.
Yeah, it makes total sense. I mean, I've spoken to many people in the cancer realm, and you're right. They would rather people die than try something experimental, even if they're about to die. It makes no sense at all. So I'm with you there. I totally understand.
Yeah, I only understand agency and autonomy, and that means, your control over your body. And to me, it's crucial. It's absolutely crucial that you have the ability to make some of these decisions, but most of the public is not educated enough to make these decisions. And so they go on using technology that we already know the outcome. It's failing technology. Everyone is dying on it. It did bring us so far, but now it's time to make a great switch. So when you look at something like advanced cell technologies, more people die every day in the United States taking their prescription drugs as prescribed, having adverse drug effects than have ever died in the regenerative area combined.
It's crazy. How many more? I mean, 10 times more, 100 times more? Or?
Yeah, it depends on the day. So, we have a failing drug system that's trying to treat symptoms, but it's causing, when you take up the difference between the technology that we're going to talk about today, gene therapy, creating a protein right at the cellular level, a protein, a human protein that your body benefits from, the difference between that and taking a small molecule that might damage your liver, hurt your kidneys, but have some off-target effect of, lowering something in your blood that may or may not be beneficial to human health. It's just the wrong way to do things. And we have the opportunity now with participation, advocation, and sharing information to actually, speed this up exponentially. So in our lifetime, we can see the benefits.
Okay. So tell me about the technology that you've been working on. What are some of the specifics of it?
Right. So we work specifically in the area of gene therapy. So after doing the work in stem cells, and after seeing my son diagnosed, we were already looking at genetics at that point. In 2003, the first whole genome was analyzed, and the medical area was really excited about the changes we could make, and we'd already seen it in our food. So a lot of people say, they don't like GMO food, but all food is GMO, whether it was bred a certain way or spliced with other things. And now, the GMO area is just speeding up that sort of change in food. But there is no food that we eat today that looks like it did when we found it. And so, so what we could do is we could actually look at model organisms. We could look at both the plant kingdom. We could look at model organisms in research, and we could see the immense potential for modifying genes, which has been looked at since the 1970s for humans. And we could see the failures over time. We could see the failures in the 1990s, but today we're not seeing those types of failures. The process has been streamlined with vectors that don't cause immune reactions, and we're more succinct and exacting with the specificity of the genes that we'll be using to actually treat the diseases. So the technology that we're specifically looking at is gene therapy, and our company specifically looks at genes that upregulate regeneration. So what does that mean? So aging is cellular degeneration over time. It's the simplest way to put it. There's 9 hallmarks to aging. They range anywhere from telomere attrition, the telomeres, the caps of your chromosomes getting shorter and shorter with each cellular division, to mitochondrial dysfunction, to cellular signaling and things like that. So, but essentially what it is a more and more dysfunctional cell over time. Now, with gene therapy in cell culture and animal models, and in some cases now, some of these are in humans, we're looking at upregulating human genes that make the cells not only act young, but look young too. And it's in its early stages now. We actually need to learn how to target the whole body, but this is the promise of gene therapy. So why would we look at regeneration? Are we just wanting to create youthful skin? Well, no, it's not an aesthetics. It's really more of a survival. So when your cells are young, they clear damage, and you don't accumulate the problems that lead to things like cancer, which is genomic instability, or things like Alzheimer's, which is the inability to clear junk potentially from the brain, although it has a myriad of other mechanisms that are just not looked at as strongly as that. And so when we look at the drug industry, they look to create a drug to treat the symptoms of something like cancer or cardiovascular disease or Alzheimer's. But the truth is, we can actually create a drug that just targets aging. All those conditions are cancer, heart disease, kidney failure, go all the way down the list. Type 2 diabetes is the effects of an aging cell. So they're considered diseases, but they all stem from biological aging. So if you treat biological aging, we would get the biggest bang for the buck. And one way, really quick, to explain what this means is because everyone's like, well, we want a cure for cancer, and wouldn't just curing cancer be easier? It actually isn't. And if you just cured cancer, for you and me, that means the life extension of about 2 years. That's it. Most people over 65 have 2 or more diseases of aging because it's accumulated damage. So most people will have heart disease and some variation of kidney failure and some form of dementia starting to rise. That's cognitive decline that we see over time. That's why people who are 20 function better on tests.
So since there's 9 hallmarks of aging, drug companies so far, I mean, at best they would try to tackle one and use one small molecule to tackle one hallmark. Are you looking to tackle all 9, or are you looking to tackle one hallmark but with a stem cell type application or genetic modification application?
Yeah, so we will look to tackle all 9. Not one gene therapy is going to do that. So I think the future of treating biological aging will be a handful of genes. Right now we're working with, BioViva is working with Rutgers University, and we're looking at a viral vector that could essentially insert 5 to 7 genes at one time. So we know it's going to be a multi-combinatorial effect. So we're looking at 5 to 7 genes, and then we'll be looking at things like exosomes to upregulate regeneration in patients. So if you think about this, if you could think about a gene therapy lasting anywhere from 5 to 20 years, you would come in and you would take an IV and you would have your gene therapy dripped into you, in which you would just sit around for a few hours, and you'd spend a couple days maybe on a immune suppressor, making sure that you don't have a bad reaction. And then the course of your upkeep with your medical doctor would probably look at 2 to 4 times a year exosome treatments. And exosomes, what I mean is the little proteins, the delivery that stem cells would do to your system, like a stem cell treatment without the stem cells. So it would just be, you would take a few injections and it would upregulate regeneration in your body and keep your body in a homeostasis. We cannot foresee the future, but that's what it appears to look like, because even the most promising genes that we're looking at right now only tackle 4 or 5 at most of the hallmarks of aging.
Are you thinking to add genes, or are you thinking to look for damage and repair it to its previous state, or are you thinking to remove certain? I mean, I just wonder how you would add genes and what if we understand truly how aging occurs. Do you think it's because genes are being deleted or snipped out or just damaged, or wouldn't we want to go in the opposite direction? If the method is damage, why not repair the damage versus trying to add genes, for instance?
That's a really good question. Thank you for asking that, because that brings me back down to like some basic premises that the listener might not understand. So when we are looking at genes that create upregulation, you're saying how could these be human genes and then unsubstantial? They're not working. So, for instance, the telomerase inducing gene, the gene that makes your telomeres long, is already in all of your cells, but it's turned off. In evolution, for some reason in humans, it turned off in all of our cells except for our germline cells. So it makes sure that your sperm and my eggs create the most youthful, viable, protected offspring. And when people don't have that, their children are born with short telomeres and they have medical problems. It's actually not good. So our germline cells, our sex line cells, have telomerase turned on in them. The rest of the body does not. And we don't know why that turned off, but we can guess that it literally is a roll of the dice, and it's not. It doesn't necessarily mean that it was the best outcome. So some species who have telomerase turned upregulated, like lobsters, live almost indefinitely. They either get too big and they get predated because they can't hide anymore, or they get like little infections under their shells, not related to telomerase. Nothing, we don't know a gene outside of genes that create antibodies against disease, which is something we can talk about later if you want to. There are genes that you can upregulate that would protect you against Ebola, but those are not genes associated with long lives. They're associated it could be, definitely not dying of disease. It's great. So we're looking at genes that are not turned on or upregulating genes. So one thing that we can do that we're known for is increasing patients' muscle mass. So we have a gene, it's called follistatin, and it's delivered, and it blocks something called myostatin, which is a muscle regulator, which becomes detrimental as you get older. Your muscles waste. If you block myostatin, you actually have an increase in muscle mass, and that's actually a gene therapy that's been through all the animal models, and with a different company, it's been through safety and efficacy for muscular dystrophy. So it has a multitude of uses, and it definitely works. So we're looking at human genes that we either upregulate, we give you more of the protein that the gene is naturally producing, or we turn on in your cells where it's been turned off. And how we do that, so this is not, scary science, and this isn't, the advancements in CRISPR. Everyone's heard of CRISPR, and that's gene editing. We don't do gene editing today because for decades, regular gene therapy that we use has been around, and it's always good to use technology that has been around because it's considered safer. What we do is we create a gene therapy for a patient, and it essentially is wrapped in a delivery method. And the delivery method can't get you sick. It's just a delivery method that targets cells, and they're targeted towards certain cell types. So if we were going to give you a myostatin inhibitor, we'd use a vector that actually is targeted towards muscle tissue, because it will hook up with the muscle tissue, and then it will deliver the human gene. And we don't integrate it into your chromosome. We create what's called an episome, meaning that it's a little string of DNA that just goes into the nucleus, and it codes for the protein that we're looking for. The one thing is, if your cells divide, it probably will not divide with it. But if we're targeting something like muscle cells, those cells tend to stay around for about 10 years. We can have a pretty good idea that you'll have this upregulated for a number of years. And so we're just upregulating a beneficial protein. So, a lot of people, when they think of what's inside the nucleus, they picture these X's, and those are all the chromosomes, and then picture right next to it a little snippet of your gene that's either lengthening your telomeres or making your muscles stronger, or in the case of Clotho, regenerating your kidneys.
It seems like if you would have a Pareto of therapies, because you can't just attack with 9 therapies or use 9 therapies right off the bat. There's so much to be known. But if you were to pick which one to work on, it seems more risky that if you picked one where, all our somatic cells have this, telomerase maker turned off, versus one where, as we age, something's happening inside a given group of cells that is, maybe it's an epigenetic change. Maybe something now is being turned off or downregulated, and reversing that. Because it's just me. I mean, who knows? But doing something that fundamentally is one way throughout a person's lifetime to reverse aging versus something that, again, breaks down or gets downregulated or stops
during their lifetime that you can turn back on seems a bit safer and less disruptive. And what are your thoughts there?
Well, that's a good question. So what BioViva does now is BioViva just does bioinformatics. We don't treat patients, but we have a partner company called Integrative Health Systems, and it actually does give patients access to medical doctors who will do these therapies. And right now, we do look at these therapies independently for the most part. There are some dual gene therapies, but we're certainly not putting 9 and 10 genes into humans. That's something way down the road. That's when we know how each one of these therapeutics affects the patient and what the outcome is. So as far as epigenetics, generally with epigenetics, over time you turn on more genes than not. And the reason that we like telomerase is multifold. One is it creates healthy cellular divisions. Number two, in animal models, it never increased the risk of cancer. And in cells, it creates genomic stability. So that epigenetic change over time that you see in an aging population is something that we would like to avoid. We do not want random genes turning on, and I'll tell you why. This epigenetic system of genomic instability leads to cancer. So that's why we see cancer rates going up exponentially, especially after the age of 85. They're huge in the population at that point. So those sort of epigenetic changes is what we would like to stabilize. But then, of course, with gene therapies, we would like to create the next level human that is more than just a genomic profile of a youthful human that already exists. We know that youthful humans are accumulating damage. That's how, you didn't get from 20 to 80 and all of those changes without things happening. There's damage that's occurring once you're born. There's telomere shortening is happening whilst you're still in the womb due to cellular division. So we need to create a substantially robust human that stays in homeostasis. And certainly we're not going to do that by throwing 9 genes at a person at one time. It's really one gene at a time, understanding the mechanisms, and then moving on to combinations.
Yeah, I like what you're saying about the myostatin inhibitor, because you could take a population of cells, not the whole body. You can, do some alteration there. There's really no reason, or hopefully, it wouldn't spread to the rest of the body. So any potential effects really would be limited to that population of cells. It just seems like a much smarter way to do it. So, it sounds like you're on the right track.
Yeah, the myostatin inhibitor is, I would say we'll understand it better in 10 years. Why I wouldn't talk aggressively against a multitude of genes in one human is because we know that not one of these gene therapies will create the human body that we need. So, for instance, in animal studies, telomerase induction increases lifespan by about 24%, and that's really fantastic. We know that the myostatin inhibitor does just about as well. I think it might even do better than telomerase by a little bit. It increases lifespan. It appears that increased muscle mass is associated with increased lifespan. Clotho in animal models extended animal lifespan by about 30%, and they were more intelligent and suffered less from things like kidney failure. So, I guess the question you're posing is combining that, would that create a better situation, a better outcome, or not? Well, that's something that we'll find out down the road. Now, I know that if I took a myostatin inhibitor, which I did, I wouldn't say, well, that's the only therapy I'll take in my life, because even though it might extend my lifespan and extend my ability for higher performance right now, certainly it's not going to extend it as long as I would hope so for. I would like a more unlimited future for humans. I mean, we're not really, as a company, trying to break lifespan as much as we're trying to create health span. But I don't want to just be healthy for 4, 5 extra years. I want to be healthy for 10, 15, 20, or an unlimited amount of years. And so we're going to have to be pretty aggressive about this. So the idea of trying a multitude of genes over time and succinctly working this out, that we can do it as quickly as possible while still gleaning information and understanding what we're doing, is going to be really important.
Yeah, I'm thinking about the psychology of, I think people tend to treat themselves like a car. My muffler is
is broken. Let me get a new one. Or my engine needs to be fixed. My heart is this. My liver is that. I don't really hear very often that someone says, I just want to upgrade everything and fix everything and make myself young. It seems like that is a wish, but the reality seems to be that, again, people just think, oh, this is broken. Let me just get it fixed if I can, and then I continue on.
Yeah, and with today's medicine, the mainstream medicine, that most of the things that you'll get for your doctor, that you'll say, oh, my kidneys have a problem, and they'll give you something that will maybe slow the process, but it will hurt you somewhere else. And statins are one of those drugs that we look at where, as far as stroke, they help 1 in 164 people, but as far as causing type 2 diabetes, metabolic disorder, they actually negatively affect 1 in 4 people, and 1 in 10 people will get dementia from the drugs. So we can't, just trying to fix one area of the body is probably a bad idea. And there's a great graph that shows where technology is and where human understanding is, and that is my job. Technology always lays way above where we're at, and public understanding lays well below that. And it's just steeped in myths, thinking that, gene therapy might not be a natural process. Actually, gene therapy is such a natural process that I can almost guarantee that you got one this year. If you got a virus, you got a gene therapy. So we're just harnessing the power of things that already happened to us. So you can see when people lived and how long they lived based on the viruses they integrated over their lifespan. So gene therapy is a totally natural process happening to you, but we're just saying let's actually design it for the benefit of humans. And it has historically had benefits. So now it's believed that our ability to be cognitive actually came from a virus that we got a long time ago, and it actually helps us with memories and thinking forward. It's the ability to carry babies to term is thanks to a virus that we integrated a long time ago, and then it protected the fetus from various attacks that used to be more common on the pregnancy, and the list goes on and on. So there are actually benefits to the viruses that we see every day, but self-evolution and creating the genetic backdrop of what we need is it's just really an intelligent thing to do. And when people start to learn about it, at first they seem kind of resistant, and their resistance are usually in the most absurd areas. They're like, oh my God, but what if everybody lived young forever? Can we actually support this? And it's like, that's actually a really good problem to have. And we're a long ways from actually solving that problem, regardless of what you read in the newspapers, because everything is fantastical. So if we don't, and we're nervous about how we're going to deal with a bunch of young, viable people on the planet, which actually, as other technology moves forward, doesn't seem that it will be a problem at all. We're already stopping ourselves with dumb questions they're not dumb questions. They're questions that need to be answered, but people will work on those. And we're stopping ourselves from actually progressing and getting something done. And then those people, even though they feel like technology will happen in their lifetime, what they will see is it will not happen in their lifetime because of their mindset and the mindset that they propagated. So there's, the people that come to our company and our partner company are people who don't believe in those myths. They want the 1 to 10 to 20% advantage over other people, and they're going to get it. It is their genetic future, and they don't live by the myths that hold them back that the rest of the population lives by. And so, my job is to try to elevate everyone to understand the benefits here and the potential. Do you want to take an infusion of a gene therapy for a gene that actually, that when certain bits of the population, small bits of the population have this gene, don't get cardiovascular disease? Or do you want open heart surgery in your 50s or your 60s when your body has an incredibly hard time healing? Most people would opt for the gene therapy, and it will become so ubiquitous and commonplace that we won't even consider it to be odd. But you have to get people over their myths to help them understand that.
Yeah, that makes sense. I think you said earlier that you actually tried the myostatin inhibitor.
Yeah, so I did both the telomerase inducer and the myostatin inhibitor. And I'm actually, so it's been almost 4 years, and I am preparing another gene therapy. So I will be looking to take another gene therapy, hopefully by the end of this year.
Well, what was your experience when you had them done? What have you noticed? Do you feel any
Yeah.
different? Or?
So what we did is we ran a bunch of tests and we saw increased muscle mass and decreased white fat, which we would expect from increasing your muscles. That also reduced my blood glucose levels by about 25%. So you increase muscle mass and you increase insulin sensitivity. So we're excited about increasing muscle mass because it keeps people active longer. It could hold off metabolic disorder like type 2 diabetes. Really beneficial. Again, animals with that gene therapy lived longer. So there's a myriad of benefits there. So we did see changes there. I want to see bigger changes. So we work on a different construct than the one that we originally used. I'd like to see a world where we can take obese people and make them fit. And then when they're fit, when they have less fat on their body and it's safe to, they can start exercising again. You have to move in order to build your muscles, even if you have a gene therapy. But I would like to see where we can safely get these people into the zone of exercise without putting them at risk of, cardiac failure or something. And the other one was a telomerase inducer. And what we saw with it, since I did both gene therapies at the same time, there's some confounding in the outcomes. But for what the gene therapy does in cells and in animals, we're attributing these benefits to it. So we saw a 50% reduction in triglycerides, which should mean better heart health. We saw my lengthening of telomeres in my white blood cells. So those are the only ones that they measure, and they lengthened by about 30 years over the last 3 years. They were critically short. Actually, my family is not long-lived, so it was not unexpected that in my 40s, my early 40s or mid-40s when I took the gene therapy, they actually measured in at the average length of a 65-year-old already. The second test, about a year after the therapy, showed that they were about my actual age, which was around 45. And the third test put them in my late 30s. And now I'm in my late 40s. I'm 48. So that was really great, but that's only my white blood cells. So I'm not going to pretend that right now with this technology we can target every cell in the body. We're working on that, and that seems to be the next big step. But we were really excited about that. What else did we see? I know that there were other changes, but I'm literally trying to think of these off of the top of my head. So the triglyceride levels, the blood glucose levels, my C-reactive proteins, which is a sign of inflammation, they dropped about sixfold, and they were in a natural range to begin with. Now I need to get them taken again, to see if the therapy has worn off. I definitely don't think that we entirely cured aging. I know we didn't. Actually, I'm still aging, but hopefully I'm aging at a slower rate, and with the next bout of therapies, we'll do more damage to aging and reverse more of the biological effects. That's our hope.
So did you have to go offshore to get these therapies done, or were you able to do it because it's an N of one? It's just you, and you were able to make that choice?
Well, I did go offshore. Through our partner, Integrative Health Systems, patients they can see doctors in the U.S. if they want, but they do go overseas to take the therapies. They go to South or Central America, depending on the clinic that the specific doctor works in. We have six doctors right now. They can choose their location. They can choose their doctor. Most of them use our U.S. doctors, and they travel with them, and they take the therapy, and they really like the experience. So as far as efficacy, it will take us years to fully understand what the therapies are doing, but so far they appear to be safe, meaning that our patients haven't been harmed by the treatment. And now we're looking for the myriad of benefits that we see both in animal models and in cell culture in these patients. And of course, we're looking for outcomes that in the myostatin inhibitor we see in patients with muscular dystrophy, the increase in muscle mass. So they do them because they want to pioneer technology, because they want an advantage, and they also do it as an experience. And so it's very cool. They're the neatest people you would ever meet. Okay. They want to create a better world for humanity. They want to participate in the experiment of creating a better world rather than continuing to be part of the medical care experiment that we know exactly how it ends.
Mm-hmm. Yeah. Well, very good. We're close to being out of time. What's the best way for people to find out more about BioViva and maybe to get in contact with questions or follow-ups? What's
Sure.
the best way for them to go from here?
Sure. So with BioViva, you can come to our website. It's bioviva-science.com. We have some testing there. We're going to be launching our bioinformatics repository towards the end of the year. It's a place that you can come and store all your multi-omic data and help cure aging at the same time, which is really awesome. We're hoping to get out a multi-omic kit soon, which is great. And then if you can go through from BioViva to integrated-health-systems.com, and that's our partner company who brokers therapeutics. You can pay to meet with a doctor and talk about potential therapies that you may or may not want to do, and get an invoice and see how much that costs and whether you want to participate in that. And so it's actually quite revolutionary.
Very good. Well, Liz, thanks for coming on the podcast. And, looking forward to seeing what BioViva will come up with. There's a lot of work to do, but you're on a good track. So thank you so much.
Yeah, thanks a lot.
You're listening to the Future Tech Health Podcast with Richard Jacobs. Until I reached age 40, I never realized the obvious, that we all have medical issues, or we at least have a family member or close relation that has, or will have them in the future. Medicine and biological systems are the final frontier. Until we've conquered death, figured out how life began, cured cancer, and understood our purpose in the universe, there's a heck of a lot to talk about when it comes to our health. Future Tech Health means I'll be covering futuristic topics that are actually already in clinical trials, or even starting to appear on shelves or by prescription, or available for your own use. We dive deep into stem cells, CRISPR-Cas9, the science of sleep, epigenetics, medical testing, cancer, ketogenic diets, stem cells, aging, regenerative medicine, and more. My goal for you, the listener, is to learn from these podcasts. You may very well learn something that may change the course of your life for the better, steer you towards a new career, or give you insight into addressing a serious medical problem. Remember, however, this podcast and its content is informational in nature only. No medical, tax, legal, financial, or psychological advice is being given. If you enjoyed the podcast, please listen, subscribe, like, and share it with friends. Thank you.